Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. In this session, we are going to study the moment of area method. What is moment of area method and why should we use moment of area method? Moment area method. The moment area method is one of the most effective methods in order to calculate the displacement, bending displacements of the beams and frames. What is the meaning of bending displacement? The meaning of bending displacement here it is the deflection of a beam of frames when the load is acted on the beams. Now here, what is the methodology we are going to consider here? It is the methodology we consider here in this case. Consider the area of moment diagram. A bending moment diagram is utilized for computing the deflections and the slope of the beams, particular points along the axis of the beam or frame. Now, in comparing to there are various methods. What are the most effective methods? What are the methods are? The first method is the double integration method, and next after that the Macaulay's method, and here it is the moment area method, and fourth one is conjugate method. Each methods are having their own uniqueness in order to calculate the slope and deflections of the beams when the load is when various types of loads are acting on the beams. What are the types of loads are? The types of loads are point loads. Another name of the point load is concentrated load. When the point load is acting in the midpoint of the beam, then it is called say midpoint of the beam. The point load is acting or concentrated is acting away from the center of the beam, away from the midpoint of the beam, then it is known as eccentric loads. When the beam is when the load is acting on the beam, that means single load is acting. Suppose if multiple loads are acting on the beam, the multiple loads means again point load, number of types of different types of more than one point load is acting on the beam. Then what are the types of deflections? And the combination, if the only UDL is acting through the span of the beam, what are the deflection and slope at the different supports? And if UDL is acting at the portion of the beam, portion of the span of the beam, then what type of deflection, displacement, bending displacement takes place? Either at the supports or in the middle portion or where your UDL is acting. And the combination of this UDL plus concentrated loads, then what are the nature of the bending displacements, either upwards or downwards, and how much, what is the quantity of those bending displacements in vertical direction with respect to the frame. So there are various types of methods, but here we are going to study moment area method. So what is that? This moment area method, and another method is called conjugate beam method. So this conjugate beam method is the modification or modified moment area method. So this method is based on the construction of a conjugate beam. That means we have defined as an imaginary beam, of length equal to that of the original beam and loaded with an elastic weight, that is M by EI, where M is the bending moment of the actual beam, where E is modulus of elasticity, and I is, what is the value of the I? Moment of second, moment mass area moment of inertia, that's millimeter per 4. Here it is Newton per square millimeter. So in order to obtain the right values or exact values or correct values, we have to follow the methodology of dimensional homogeneity. So let us begin with the moment area method. Here the figure shows the two figures, A and B, figure A and figure B. The figure B having a span length L. The figure A consists of the length of the two supports B to A, B to B and A supports, and the distance between B and A is L. So here the AB beam is carrying any type of load, certain load, because we are focusing on this moment area method is focusing on area of the bending moment diagram. So whatever load may be, here the main important is the shape of the diagram, bending moment diagram. The bending moment diagram is non-linear, it's the curve, that's a parabolic curve. That we need that area. If the bending moment is linear, when the point load acts on the beam, the bending moment curve comes linearly, it varies. So it is easy because it is in triangular shape of base into height, area of that bending moment diagram. So the critical point here it is that we have to calculate the area of the bending moment diagram. That's it. After that you have to substitute in the formula, then we'll get it. Alright, now what is the bending moment equation? What is the slope and deflection equations? Now, due to the load, now the beam is there simultaneously we are going to explain in relation to A and B diagram, both the diagrams. Now here the figure A, that the figure A is shown that a bending moment subjected to bending moment, and the beam is bent into the, what is the beam, how the beam is bent? A, Q1, P1 and B. A, Q1, P1, B. The beam is bent in that shape. Now, due to the load acting on the beam, let A be a fixed, A point be a zero slope and zero deflection we assumed here. And at the same time, we consider an element PQ of a small length. The length of the PQ element is dx. Dx is the element length, PQ. At a distance, what is the distance here? The distance x from B. This is the distance x from B portion. And here, the corresponding points on the deflected beams in the diagram is P1 and Q1. Corresponding points are P1 and Q1. Next, what is the R here? This R is the radius of curvature of deflected part P and Q. P1 and Q1. This R is the radius of curvature. Now what is d theta? The d theta is the angle subtended by the arc P1 and Q1 at the center O. What is the M? M is the bending moment between portion PQ. This M is the bending moment between the portion PQ. What is the P1C? This P1C is the tangent. This is the tangent at point P1. This P1C is the tangent at point P1. What is the P1O? This P1O is the normal to the point or to the tangent P1C. Next, if we consider another, what is the Q1D? The Q1D is again tangent at Q1. Tangent at Q1. So this tangent P1C is the tangent at P1. Q1D is the tangent at Q1. The normal to the Q1D tangent is Q1O. The normal to the P1C tangent is P1O. Now, the angle between, what is the P1Q? P1Q1 equal to R d theta, arc length. That is the distance between, that is the between dy. This is the slope between P1Q1, two tangents is dy. Now the tangents P1Q1 are cutting the vertical lines through B. Cutting the vertical lines through B at points is the B is the vertical line at points C and D. At points C and D. The angle between the normals P1 Q1 will be equal to the angle between the tangents P1 and Q1. These are the normals. The angle between the normals the angle between the normals at P1. What are the normals are here? P1O and Q1O. The angle between these two normals is what? D theta. That equal to the angle between two tangents. What are the two tangents are? P1C, another tangents, and Q1D is another tangent. This is the same angle. D theta. Alright. Now what is the arc length P1 Q1? This is the radius of curvature R. This is the portion D theta. That means R D theta is the portion. That P1 Q1 equal to R D theta. That R D theta equal to what? That P1 Q1 is nothing but, come on, P1 Q1 equal to what? Dx length, element length. Dx equal to R D theta. Now, D theta equal to dx by R. Coming to the concepts of theory of pure bending, you see how it is useful. The theory of pure bending is M by I equal to E by R. What is the pure bending equation? M over I equal to sigma by Y equal to E by R. From that, we have a relation between this modulus of velocity and radius of curvature. That's why these two portions you have to consider. That is M by I equal to E by R. What is the radius of curvature from this equation? R equal to E I by M. Now d theta equal to, we know the dx by R. In the place of R, substitute E I by M. That is M dx by E I. That is the d theta. You might have understood what is the d theta again. It comes under the slope. What is the slope we want? Theta equal to, it is varying from 0 to L, span from 0 distance at point A to L distance up to B. So 0 to L M dx by EI. That is 1 by EI times 0 to L M dx. This is the theta equation. So now M dx represents what? Area of the bending moment diagram. Area of the bending moment, M into dx. M is the bending moment value, vertical, and horizontal x value, area of the bending moment. So area of the bending moment diagram, that is the M dx. 0 to L times, this 0 to L times M dx represents significance of 0 to L M dx is the area of the bending moment diagram. Now what the slope comes? Slope equal to 1 by EI times integral 0 to L M dx. The 0 to L M dx is nothing but area of the bending moment diagram between A and B. So we want slope at B, that is theta B equal to, theta B means, what is the slope at B? Slope at B equal to area of the bending moment diagram between A and B by EI. This is the slope we calculated. What is the next we want? We want a deflection. How to find out deflection? We'll see. Now here, if the slope at A is not 0, then we have one more important here. If the slope at A is not 0, if it is 0, then theta B. If it is not 0, then what to do? Then equation becomes theta B minus theta A equal to area of the bending moment diagram, bending moment between A and B by EI. What is that EI? So far we did not touch. This EI is nothing but flexural rigidity. Okay. So that is the theta B minus theta A. That means total change of the slope between B and A. If it is A equal to 0, that means there is no slope. Then theta B. Then what is the slope changing? Slope means changing and variation. The slope means variation of the curve. How it is varying. That is nothing but tan theta equal to dy by dx. So that theta, how the variation is going on, variation of the displacement, variation of the deflection indicates in the form of the slope. Now theta b minus theta b, that is the change of slope between b and a, is equal to area of the bending moment between a and b by ei. Alright, that is the slope. Now first portion was over, calculated the slope. What is the second portion? The second portion is, we have to go for here how the deflection. The second is that calculation of the deflection. So now the deflection due to the bending of the portion P1 Q1 is given by what the dy equal to again x d theta. So dy equal to x, what is the d theta value? Yes, the deflection, let us go back, this is the dy. We want dy, what is the distance from here to here? That is the x, this is the d theta. X times d theta gives dy. So simple. From the dy equal to, what is the d theta? M dx by ei. Now y equal to integration 0 to L times x times m dx by ei. Make it ei is the constant 1 by ei, x times m dx. What is that x times m dx? This 0 to L, m dx indicates area of the bending moment diagram. Okay. So now, what is that area of the bending moment times again and again distance. That is the moment of area of the bending moment diagram of length dx about point B. Now 0 to L xm dx indicates moment diagram A times, that is the area of the bending moment A. What is x value? Integral 0 to L A x bar. A x integral 0 to L x here means that is A x bar. A x bar by ei. What is it? A here, capital A letter indicates area of the bending moment diagram between A and B. Bar x indicates distance of CG, center of gravity value from A to B. Okay, this is the deflection value, A x bar by En. And another value, theta equal to, what is the theta value? Theta equal to area of bending moment diagram, area of the bending moment, A by ei in simplification. Area of the bending moment diagram between A and B. So now the relation, if we understand, y equal to deflection equal to A by ei times x bar. This A by ei means theta. Can we make it like that? Theta times x bar. That's what we understood here. Now, if you want to understand that area here, the deflection involves the slope. That's why slope is the part of the deflection. Otherwise, how the deflection is maximum, deflection is minimum, deflection is zero. How to make it? Now here A x bar by ei means what is the area of the bending moment, and also we want the distance from the center of gravity, distance, the central distance from support A, that is bar x. And what is E for? The value of modulus of elasticity of the material, and I value is the second moment of area, moment of inertia of the section. If it is a rectangular section, if it is square section, if it is C section, if it is H section, Z section, we have to find out the value of the I parallel to x-axis, that is about neutral axis. If we know area of the bending moment diagrams and the value of E and I, then we can calculate directly what is the slope and deflections of various beams under various loads. Now here, the deflection and the slope of a cantilever beam. Now we are going to find out by moment area method. Now the case 1 we considered here. What is the case 1? We are going to find out moment area method. A cantilever beam, case 1 here, carrying a point load or concentrated load at the free end. First again, we have to know we have to draw the bending moment diagram. not shear force diagram here, not required. Shear force diagram is not required. The bending moment diagram is required. So draw the bending moment diagram based on the values, based on the loads. Now, the bending moment diagram for a cantilever beam subjected to a point load at the free end is the shape of the bending moment diagram. So, in order to find out the slope and deflection, what is required for slope? For slope, area of the bending moment diagram, area of bending moment diagram by over EI, E times. So, the bending moment will be 0 at point B, and it is W times L at point A. So the variation of the bending moment from A to B, how it is varying or is linear, it is shown in figure. It is maximum at fixed and it is 0 at B. It is linearly varying. It is the shape of the bending moment diagram, BM diagram is, BMD is your triangle. For a triangle, whereas in the calculating the deflection, we need the central distance from support B to A here, from 0 to maximum. That is here 2x by 3. 2h by 3 means here L we consider that is 2L by 3, and here from this here L by 3. So from this value, that is x bar x, and one more value required, A value. What is the area of the bending? What is the area of base into height? What is the base of times, what is the base? W times L, height L. WL square by 2. Let us begin here. At the fixed end A, the slope and deflection are 0. But theta B, slope at B, that is dy by dx, slope at B, that is dy by dx at B. At a fixed end A, the slope and deflections are 0. There is neither slope nor deflection. But we want at B. So YB is the deflection at B, at theta B is that slope at B. Now theta B equal to area of the bending moment diagram BMD between A and B by EI. What is the area of the bending moment diagram between A and B? It is a triangle, right angle triangle, that is of base into height. What is the base? AB, height is AC. Now of base L into height WL by EI, that is WL square by EI. That's it, simple formula we got. If you substitute the value of the W and value of the L and values of E and I, we'll get it theta B. Alright, theta B values. Next, what is the next one we need? We need a deflection at B. YB, A x bar by EI. Where A is the area of the bending moment diagram, bar x, the distance, centroidal distance from 0 to the centroid here, central distance, that is 2L by 3. So, what is the A area of that one? We consider area of the bending moment diagram is of base, WL times, base is L and WL times L, that is WL square by 2. WL square by 2, substitute here, and B x bar x value 2L by 3. After substituting WL square by 2 and 2L by 3 by EI, that is WL cube by 2EI. WL cube by 3 times EI. Alright, this is the case for what is the theta A? Yeah, theta B is WL square by 2EI, theta YB is WL cube by 3EI. These are the derived formulae for calculating the slope and deflections of a cantilever beam at the free end, where the point load is acting. Next, case 2. What is the case 2 here? A cantilever beam carrying a which load? Uniformly distributed load. Yes. And throughout the span of the beam. Again, what to do? First, we have to draw the bending moment diagram. Calculate area of the bending moment diagram. Another one. The distance, the central distance of the diagram from the free end to fixed end, from 0 to wherever, maximum. That's it. If we know these two values, after substituting, theta means what? Area of the bending moment diagram by EI. What is the deflection? That is A x bar by EI. That means area of the bending moment diagram, bar x value and EI. EI is constant. We need two parameters here to find out the slope and deflection. by using moment area method. What are they? Number 1, area of the bending moment diagram. Number 2, parameter 2, what is the centroidal distance from the fixed, where from 0 to max here, the central distance. If it is the free cantilever beam, from free end to the central distance. Alright, that is the bar x value. Now after drawing the bending moment diagram, alright, this is the bending moment diagram will be obtained. But what is the variation? The variation is not linear, it is non-linear variation. But we have to find out. So bar x value comes for this type of variation of the beam, this 3L/4. And what is the area? This is the variation, that is how much value? Area here WL²/2 times L. So the area of the bending moment diagram, that is WL3/6. Let us see here. So the area of the bending moment diagram ABC, that is A equal to of base into, again it is considered not as a triangle. So this is the formula for this, 1/3 of here L times WL²/2 variation, 1/3 of base into height, that is WL3/6. Now x equal to 3L/4, area value WL3/3, where here the small w is what? Uniformly distributed load. Now substitute area of the bending moment diagram by EI, area of the beam, that is WL3/6 EI. What is the deflection? AX bar times AX bar by EI, that is WL3/6 EI, A by EI, a bar x 3L/4, that is WL/4/8 EI. These are the derived formulae. So these are the various formulas we have derived for these cases. So what is the difference between the moment area method? We solved only in this session moment area method. We did not use any double integration method or Macaulay's method. So far we have calculated in before previous problems. But in this problem, moment area method having certain uniqueness and certain difficulties. The uniqueness is very simple. If we know the substitution, what is the theta b and yb simplified here, that is area of the bending moment diagram by EI, that is flexural rigidity. And deflection comes AX bar by EI, that means AX bar by, what is by here? EI means flexural rigidity. But the flexural rigidity E and I are constants, but whereas the bending moment diagram and the central distance are important, bar X. This, if we know the area of the bending moment diagram and bar X values, we can go for it. But the most practically here, how to find out the non-linear curves. For triangle, you see, very simplicity. If the bending moment diagram is triangle, it's okay. We can get it out base into height area. If it's the different non-linearities are there, then how to find out this area? It is not direct formula. We have to go for integration 0 to L, finding out the area of the element length, go for it. So that is the difficulty in the case of moment area method. So my understanding here, to find out the slope and deflections of various beams at various points loads and various supports. So if we, this much difficulty is not there in the case of Macaulay's method. In the Macaulay's method, very simple. If we find out the distance, the bending moment equation, if you know, and apply the same boundary conditions for every problem where supports, consider the supports and can apply the boundary conditions. It's so simple. So there bending moment equation, substitute and integrate once, deflection equation comes, and if we integrate the slope equation, deflection equation comes. After getting those two equations, derive the constants of integration by using the boundary condition. That's it to our substitute x values. You'll get it at different values of x, at different values of slope and deflections. Alright. But whereas in moment area method, although simple, but provided one has to having abilities to find out the area of the bending moment diagram and also find out the bar x values, x bar value. If you know these two values, substitution directly will get it, the slope and deflections directly for any type of beam. But it is simple, it's okay. For cantilever beam, it is easy, it is applicable mostly. Whereas the multiple loads are there, the combination of the loads, The total area is required is complexity. That is the challenging job for an engineer to calculate the slope and deflections by using moment of area methods in comparison to the Macaulay's method and W integration method. So, and why should we use moment area method? We already discussed. And what is what is the difference between conjugate method and moment area method? This conjugate method is the modified form of a moment area method. All right. So these are the various methods we discussed in previous sessions, past sessions, and onto present session. Now here, and one more thing, what are the things knowledge is required for solving the slope and deflections of various types of beams? The knowledge is that, number one, the knowledge of shear force and bending moment diagrams for calculating the support reactions. And another is that theory of the pure bending. So that means the variation of bending stresses across the section of the beam. And one more, the knowledge of calculation of second moment of area, that is called area moment of inertia values for various sections of the beam. For that, again, if you go to the deep, we should have a thorough knowledge of applying the parallel axis theorem. So these applications of calculations of area moment of inertia and parallel axis theorem thoroughly you have to practice in the course of engineering mechanics. All right. Yes, these are the references, textbooks and web references are followed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.